the source, and this obviously delivers you.
Going to talk about another experiment, BeamEDM, and looking forward to your talk, Florian. Thanks.
Thank you. Thank you, first of all, for the invitation. I had the pleasure to be here already 3 years ago, where I presented you some of the ideas of this experiment. Now I can show you a bit more concrete stuff. And I want to show you a little bit beyond the BeamEDM experiment. So the BeamEDM experiment, you heard talks by Kent and by Philip now and by Tito. These are all neutron EDM experiments that use ultra cold neutrons. And the idea here is to go back to the roots and use a beam of cold neutrons instead. So just to give you an overview, if you're not so familiar what we're talking about, so far you've heard about these ultra cold neutrons, which are used, which you can nicely store in bottles and for instance at PSI or in Los Alamos at various places where they have dedicated sources. They are so slow they can be stored. While there's other sources, for instance, also at PSI or at the Institut Langevin or in future at the ESS in Sweden, where you also have cold and thermal neutron beams. So these are much faster. They are still very slow compared to what you know from maybe Large Hadron Collider or so on, but they are on the order of 1,000 meters per second or 2,000 meters per second. We are looking into these ones that are so-called cold neutrons. So they are moderated with liquid deuterium, and they have a Maxwellian spectrum, and they have a peak at roughly 1,000 meters per second. So the BeamEDM experiment has started in late, that's mine, I think, sorry. In the late 2016. And then we had several beam times at PSI, like test beam times, first setting up of the apparatus and so on at PSI in 2017, 2018, and then beam times at ILL in Grenoble, 2018 and 2020. And I will show you mostly from the last beam time, 2020, where we also for the first time took real neutron EDM data. Still not with the statistics that were shown in the UCN experiments, but real EDM measurements, right? So I'm skipping all the introduction about CP violation and why EDM is important. I think we all know that, and we heard various talks about this. So I'm going a bit in the history and the plots that Philip has showed, also similar plot that Philip has also showed about the neutron EDM limit. So we know all that no EDM been found for the neutron as a function of the year of the experiment. And you see that there's somehow a jump from in the 1980s, where people before have done neutron experiments with beams, and after that using ultra cold neutrons for the various obvious reasons that we have already heard. You can store them for a longer time, you can accumulate them, and so on and so forth. And here in red and green, I showed the best BeamEDM experiment, 3 times 10⁻²⁴. And now the result that Philip has just showed is 1.8 times 10⁻26 electron centimeter. And obviously, we all want to get in this beyond standard model region to find something interesting. So the idea is now to go back to revisit these neutron beam experiments. And the question, first of all, Philip also mentioned a lot, like the central thing in all these EDM experiments is to stabilize the magnetic field, to know as much as possible about the magnetic field. So why is that the case? If you just plug in numbers, 10⁻26 electron centimeter at 10 kilovolt per centimeter, so a typical electric field, this corresponds to a magnetic interaction of the magnetic dipole moment of the neutron with fields on the order of a few femtotesla. So we are always talking about this femtotesla range. And if you think about that, your brain already produces picotesla fields, then you know how sensitive we have to be, or how careful we have to be in all these experiments. So a quick comparison between the neutron EDM sensitivities. You saw already this formula also in various talks. So the sensitivity, how the statistical sensitivity, you have to say, to the neutron EDM scales with the electric field E, with the interaction time or the observation time T, capital T, and obviously with the number of neutrons. So in the UCN experiment here on the right side, this is just the numbers taken from the publication from this, what Philip has just shown from 2020. So electric fields of about 11 kilowatt per centimeter, number of neutrons per spill or per cycle is about 11,400 neutrons, while one cycle takes about 300 seconds. This is the cycle where you fill you get your UCN, you fill them in your chamber, you measure, you let them process for 180 seconds and then empty them out again. So that gives you a rate of about 40 hertz. And then there's the storage time, 180 seconds. On the other hand, if you, I showed you some numbers which are for this experiment that I want to present you. So you can go higher in electric fields. This is due to the fact that in the UCN experiment, you have a chamber to store your ultra cold neutrons. So you have a top and a bottom lid, and then you have the insulator walls. And these insulator walls are the main limitations for your electric field that you can achieve. So already in the 70s, people have achieved 100 kilowatts per centimeter in these kind of beam experiments, even higher, like up to 130 kilowatts per centimeter. Then the statistics or the rate of neutrons, this is where you have to gain, right? So compared to this 40 hertz in the UCN experiment, you have to gain a lot because you will lose a lot in the storage time. So you will lose about a factor of 1,000 or more in the storage time. So in statistics, you have to gain a factor of 1 million to be comparable. And this is achievable with future facilities, for instance, at the ESS, where you could have 100 megahertz or so of intensity. So you basically balance out the storage time with statistics. So we have seen various ideas of the Ramsey technique. This is from the original from Ramsey in the 40s, 50s. So this is now really a beam type of experiment, but it's very similar to the UCN type. You come in with polarized neutrons. So this arrow shows the spin of the neutron. You have a region of magnetic field where we assume it's homogeneous, B0, and then you have two RF, so radio frequency pi half spin flippers, where you flip the spin by 90 degrees. And then they start processing like a clock in a plane perpendicular to the magnetic field. And then at some point later, you have a second pi half spin flipper where you complete your flip. And then at the end, you need a neutron spin analyzer and detector. So you check whether the spin is up or down. And you can then detect these neutrons. And if the neutrons, for instance, these processing neutrons, these clock neutrons, gain an additional phase, for instance, due to an electric dipole moment interaction, then, for instance, the spin here at the end could point upwards again, not downwards, or as some kind of superposition of up and down, right? And when you now change the frequency here of your two RF spin flippers, and you scan around the Lamov precession frequency, you get this Ramsey type signal that also Philip has already shown. And in the center, it looks pretty sinusoidal. And if you now would have an EDM, this would lead to a shift of the sinusoidal signal. In case that you once applied the electric field parallel or anti-parallel to the magnetic field. This can be translated here. So you have basically two different Lamov frequencies. If you have this magnetic and electric field parallel or anti-parallel, and then you multiply this by the interaction time. So the time the neutrons spend here processing, then you get a phase, and this is just this phase shift of this Ramsey signal. So if everything is in order and during these two measurements with parallel and anti-parallel, the magnetic field doesn't change, and you see a shift of this Ramsey signal, then you have would have an evidence for an EDM. And of course, this depends then on the electric field strength. So the last beam type experiment was done in 1977, and this was done also at ILL in France. And here you see a sketch of this. This was a rather compact experiment. So the beam is coming from somewhere here, from the left top corner, and then it goes to spin a polarizer, so to polarize the neutrons, and then it goes to this this chamber, which is basically a magnetic shield. Again, you see here the two RF spin flipper coils, and here two plates, which are the electrodes, where you can apply high voltage and then essentially an electric field. And then you have a spin analyzer and detector, and they were using a white beam with a spectrum peak at about 150 meters per second. So what they did, so this entire thing was about 2 meters long. You see this here, the gap was about 1 centimeter between the electrodes, and they achieved 100 kilovolt per centimeter. And then they switched the polarity of the electric field. So they performed this Ramsey experiment, the Ramsey type experiment, and then they switched the high voltage polarity every 200 seconds or so. And then they ran into problems, or they knew, of course, they will run into problems with the so-called relativistic V cross E effect. I will show you this in a bit more detail in the next slide, because this is essential for this experiment. And just to tell you how they countered this effect was that this entire setup was mounted on a turntable, which they could turn around and basically invert the velocity of the neutrons, because they once go like this through the experiments, and then by inverting the entire experiment, they went through the other way. So why is this V cross E effect important? Why have BeamEDM experiments been abandoned? And this is the V cross E effect. And you see this here nicely on the right side. So this is the effect when a particle, for instance, travels with a certain velocity through an electric field due to relativistic special relativity. It sees an effective magnetic field, which can be tiny, but is important because we want to measure small magnetic field, right? Or magnetic field effects. So this effect arises. So the green cross means that the neutrons go into the plane, into the drawing plane. And this effect arises when your magnetic field and electric field are not perfectly aligned. So there's a slight misalignment angle alpha here. And then you have a perpendicular component E perpendicular. And then if you make V cross E, you get B down, but then you have a minus sign there. So you get a small V cross E pseudomagnetic field upwards. And if you then invert the electric field, you get a pseudomagnetic field downwards. So this is exactly what you don't want. You get a magnetic field that just changes with the sign of your electric field. And these can be rather large, this false effect on the order of 10 to the minus 20 electron centimeter times this misalignment angle, for instance, for 100 meters per second. So even if you align everything very well with nice accuracy to better than millirad, you're still in the 10 to the minus 23 electron centimeter region, which is obviously not what you want. However, this has this comes in, the solution is basically already in the name, because it's a V cross E. So it's velocity dependent. This effect is velocity dependent, while the EDM itself is not velocity dependent. So you need to have a way to distinguish between these two effects, velocity dependent and velocity independent. And this is just the idea of this concept. So you measure everything that I showed you before as a function of the velocity, as a function of the time of flight. And this ideally you do in a pulsed neutron source. So you don't use a continuous source which you chop, because there you lose intensity, but you use a pulse source. And this is ideally for this European spallation source, because this will be a pulse source. But of course, we start with proof of principle experiments, and this is what I'm going to show you. And if you plot then this phase shift of your Ramsey curve as a function of 1 over the velocity, or as a function of time of flight, you will see that the slope of this phase shift will just be your EDM, and the offset will be your false effect, the V cross E effect. Okay.
Sorry,
yeah.
Suggested the experiment better be longer or shorter?
I'm sorry?
This suggests the experiment better be longer or shorter? Or
always longer, because that's well, I cannot say always longer, but the longer is usually better, because then you have more interaction time, right?
This would increase the offset, but it doesn't matter.
This doesn't matter, yeah. You can tune it. So what we did is you can tune this this alpha angle by applying not just one magnetic field, but also a transversal magnetic field, and then you can get it actually down so that it becomes perfectly flat. Yeah, because in the end, what you do is you're only interested in the slope, right? You're not extrapolating or doing something like this. You're not extrapolating. You just make a linear fit, and you just extract the slope. You don't care about the offset anymore. It's just a way to distinguish the two.
Right.
Okay, so this is a sketch of how this should look like. So as for the N2 EDM experiment or other future ultra cold neutron experiments, we use the idea of having two beams, not just one beam, and having three electrodes, not just two electrodes. So we would have a central electrode on high voltage, which we can flip the polarity, and the two outer electrodes here depicted in gray would be on ground. And then you have this pulse source. The neutron spins are polarized already, and then they fly between these electrodes. You have here these 2 pi-half spin flippers, spin analyzers, and 2 detectors or pixelated detector or something like that. And typical sizes would be, and this is also what we have built, would be on the order that this separation is on the order of 1 to 2 centimeters or so. Also some other numbers which came, well, there are some reasons why we come up with these numbers, but I'm not going into much detail here. So we work at a field around 200 microtesla. We would like to achieve these 100 kilovolt per centimeter. And in our proof of principle experiment, the electrodes were 3 meter long, and they can be 50 meter long, or we saw that already we get very good results with 20 or 25 meter long. So this is the reality in 2018. So this was one of the first beam times. I will walk you through a bit of this messy image here, where you see there's lots of cables going on and all this. The important thing here is, so the beam is coming here. This is at PSI, at the Boa beam line. The beam is coming from the very left and enters here on the very right. And because this is a panorama picture, this image is slightly distorted. Obviously, everything is straight in reality. So you see that the basic concept is that we work with 1 by 1 meter cubes. So we have a modular design. So we can, if we go to a different beam line, we can add cubes, or we can take away cubes. So all of these cubes are identical, so we can work with that. So all these cubes are just the base holding structure where we mount all of our experiment. And this, of course, has to be non-magnetic, so aluminum and plastic and copper, so are used, nothing else. Also aluminum screws, no stainless steel screws. These green coils here that you see here in the beginning and at the end, in the first and the fourth cube, these are the pi-half spin flippers. So the neutrons come in here, they get flipped, as I told you before, and then they go in this vacuum beam pipe where our electrodes sit in. And we have obviously 2 beams. You see here, there's an apertures. So you have here apertures. Before you have apertures, and in the back you also have apertures. These are just absorption apertures. And here you have a spin analyzer and a detector, and I'll show you a few things more. And maybe what I wanted to show you as well is here are a lot of coils. They are rectangular Helmholtz type coils. And we have them in any direction so that we can have the magnetic field in 3D, basically. And of course, we have to stabilize this with flux gates and monitor these with flux gates. These are these purple cables, actually. These are all the flux gates cables. And in order to have a pulse beam, because the PSI is a continuous source, we have a chopper disk that is running. And then just from time to time, that's through a pulse of neutrons with a frequency of about typically 20 hertz or so. And in the back is our detector, which is a pixelated detector. So we've soon figured out that we can work with this scenario, but we need also magnetic shielding. So in 2020, we bought these panels. So this is now a 6 meter long setup, so 6 cubes. And we have this 2-layer magnetic shield. And you see and we also characterize this. So we had here a magnetic field mapper with lots of flux gates on them, driving through the entire thing and measure the magnetic field with and without the shielding. We had some big coils in the room at the edges of the room where we could apply oscillating magnetic fields, and then we measured with and without. And we see you see here, this is a function of the length of the experiment. For various frequency for the transversal shielding factor, we get around at 0.5 hertz. we get a shielding factor of beyond 100. So, and we saw that this massively improves our signals and stability and so on. This is probably still not enough, but this is what we could afford at that time. So we built all these things in Bern in Switzerland. And of course, we need to do these experiments at ILL, for instance, or at PSI. And that's just to give you an impression. So we boxed everything. We had to take everything apart and then assemble everything again at ILL in this case. So these are like 2 trucks of load that we had to bring. You see all these cubes, we leave them assembled, but we have to bring them together. And this is also the idea, because if we would have one big experiment, we could not just transport it somewhere else. So you see there's a big hall. This is just the mu metal here, mu metal boxes, another cubes. Of course, we have to bring everything from a ladder to the screwdriver, boxes with detectors, and so on and so forth. So that's really a lot of stuff, which we have to assemble then there. And this is what you see here in August, September 2020. So you also need several students, obviously, to do all this work. We assembled then the cubes. We have to align them. We did this with a laser and also with a theodolite to really have everything straighten up, first of all. And then we had to mount the mu metal. You see, we have to take each panel out with a crane, because each panel already weighs like 60 kilos or so. And then we have to transport it through the entire hall to get it to the experiment, and then patch this thing up. And then you obviously realized, oh shit, we have forgot a cable inside or something like this. We have to open it up, or what is wrong? And so it's a lot of work. Here you see Jacob, one of my postdocs, checking the electrodes, if everything is connected well electronically. We will see a close-up later of this. Here we install the high voltage feed-through, which is kind of tricky because we didn't have lots of space there anymore, because we really filled the entire experimental gap. And this is a pit. And this is then where we look at the first neutrons and the first data coming in. This was a very nice event. So this is how, in the end, how it looks like. As I told you, we almost filled up the entire space, but then we cleaned it up to access it again, to be able to walk around it and to manipulate things and so on. So on the left, so the neutrons coming here from the back, and down here is our detector. And here's the high voltage feed through. Here's the vacuum pipe where we pump on the tubes. And here you see a typical time of flight spectrum of this beam line measured with our setup. So you see this peak at 1000 meters per second, which corresponds to roughly 4 angstrom wavelengths, de Broglie wavelengths. So we had 2 beams, each 1 by 7 centimeters. We have a magnetic field vertically pointing upwards, 220 microtesla, 3 meters of electrodes, internal and external flux gates mounted all over the place, and thermometers mounted and so on. So I want to show you a few details now. So this is the chopper that we use. This is basically a collimator. So these are silicon wafers coated with a neutron absorbing material, gadolinium, and they are installed on a fastly turning turntable. And you see that. So of course this is done by hand, but you can imagine this is motorized, obviously. And then the neutrons can pass through this, and then every time this opens up, it gives a pulse out. And we can turn this by roughly 15 to 20 hertz. So we get pulses from 30 to 40 hertz or so. And then this is installed in a big box with absorbers and so on in the casemate at PF1B. And I really like that it turned so well. So this was, it was really turning nicely. So a nice Swiss mechanical precision in our workshop. Huh? Yeah, exactly. You can do this for hours. So these are the electrode stacks. So they're 1 meter long. The separation between the electrodes is 1 centimeter, and you see in the center is the high voltage electrode. So that's why it's here insulated with these plastics holders, and then you have these 4 rings which hold the entire thing together. Then it's mounted inside the tube and the vacuum tubes, which are also 1 meter long, and then they have to be aligned and stuck together. And this is kind of a tedious task. And the electric field that we achieved stably. So we achieved like 70 kilovolts, but we had lots of breakdowns. So we reduced it. So we, in the end, we had like 40 kilovolts per centimeter stably. And then you apply the magnetic field upwards. And then because you have here the center electrode on high voltage, you get here the magnetic field, electric field parallel, and in the lower beam you get them anti-parallel. So you measure both of these spin configurations at the same, both of these configurations at the same time. Nevertheless, you still invert the polarity, so then you flick just these configurations again.
And in the previous talk, Philip was telling us how precise we need to understand both the magnetic field and the gradient. Here you don't need such precision because the electric field is stronger, or do you have some similar problem? Or?
Yes, it scales with the electric field, but we still have the same issues. Yes, but this false effect scales a bit with the electric field because you have, yes, it's basically linearly scales with it. But well, instead of 1 femtotesla, you have to be careful on 10 femtotesla levels, okay. Or something like this. But it's still it's a very difficult problem, and I mean. It's also a larger geometry, right? So yeah, I don't think it's easier.
No, I mean only the magnetic.
Yeah. So going through these details. So this is the spin analyzer here, and behind that is our detector. The spin analyzer is basically silicon wafers, which are coated with a certain material, so that one spins, some magnetic material, so one spin species gets reflected, and the other one is transmitted through. And then we have these in like a V-shaped configuration, so that we have the two beams coming in, and then we have this V-shaped configuration, and then we get on our pixelated detector, we get the reflected beam and transmitted beam of the upper beam, and then the transmitted beam spot and reflected beam spot of the lower beam. And then we send it in, so that we didn't do any spin flips or anything, or no pi-half spin flips. We just let it spin up and one spin down, and you see here the difference. So spin up configuration, the most of the intensity goes in the reflected beams, and then if you go in the spin down configuration, most of the intensity goes in the transmitted beams, just as it should be. This is then when we did the first Ramsey type experiments. And you see, we scan here the frequency of these two spin flippers. So there's two lines here, or two data sets with the bottom and top beam. And they nicely coincide at the resonance frequency of about 6,380 Hertz, which corresponds just to the 220 microtesla. And the signal is not very nice because here we integrate over all wavelengths. So we just take the entire white beam. When we do measure this as a time of flight, and we just cut out a certain wavelength, like on the right side, here 9.5 angstrom, for instance, then you get really this nice Ramsey pattern with asymmetries or visibilities up to 90%. So what is plotted here is the so-called asymmetry, which is the number of transmitted neutrons minus the number of reflected neutrons divided by the sum of both. So what we saw here, we have the reflected and transmitted beam spot, and then we calculate from that the symmetry. Okay. So this was with a white beam, but now you want to work with a chopped beam, right? So you have and then that means the fast neutrons will reach your detector earlier than the slow neutrons, and they will also reach your spin flippers earlier than the slow neutrons, and they will also spend a different amount of time in the spin flipper and also in the interaction region. So what you have to do here is to get a nice pi-half spin flip for any neutron velocity, you have to trigger your RF signals of the pi-half spin flippers and modulate them. Modulate the amplitude with 1/t, because so that the interaction, so that so that they all get a nice pi-half spin flip in the end, right? Independent of the velocity. And this is what you see here on the right. So for instance, for 3.8 angstrom, you get here this pattern, and then for 7.6 angstrom. And then what we actually did here is not that we scan the frequency any longer. So here, this was what we call classic Ramsey, where you scan the frequency. What we did here is we sit on the resonance frequency. So at this 6,380 Hertz. And then we scan the relative phase of the two spin flippers. And then you get these phase Ramsey signals. So we scan here from 0 to 360 degrees, and then we get this nice sinusoidal pattern. And then in the end, what we also do is we not measure this entire curve. We measure this for the beginning, that we know how the curve looks like, that everything is in order, but then we can basically sit on just one working point. And if now there would be a change of this phase signal due to a magnetic field change or due to an EDM or another effect, then you would see that this entire curve would shift left and right. But in the end, you would see that the asymmetry goes up and down, right? And we do this at the point of steepest slope where the asymmetry is roughly 0. So this is where the working point is shown here. And we did this, measure this for a long time, right? Well, 11 hours in this case. We always measure the same point, And then from that, because we know the shape, we can relate this change in the symmetry that we saw to a change in phase. And this here is for the top and bottom beam. And you see that over 11 hours or so, the phase changes by, well, let's say half a degree or so of this pattern. But the nice thing is that they move together, right? So in the end, what we want to know is sorry, I skipped one. So in the end, what we measure is the difference. And then we get this rather nice flat behavior. I have to admit there's something going on here in the back. So what remains is probably like magnetic field gradient changes. This is what you see here. And if I go back to that one, this is one of our temperature sensors that we had all around the place. And you see they behave quite similarly. There's a slight time change. So this has the minimum at like 6-7 hours, and this has the minimum at about 8-9 hours or so. So there's a little latency. But you have to see this entire thing was set up in August, September in France, where we had like in the experimental hall like 35 degrees or so, and there was no thermal insulation, no air conditioning or anything, right? So this was in the plain open, and then we had temperature drifts from day and night, more than 10 degrees. And for that, I think this is quite a remarkable result. Yeah, sure. Oh yes, you can. We've done that, but I don't have data to that. No. But it already by eye you see that this is temperature dependent. What actually is then the effective mechanism that the temperature translates directly into a phase is not yet clear. If this is a change in distance, like extra, or this is a real magnetic field change. This is I don't think it's really a magnetic field change because we stabilize the magnetic field also. But it could be, well, we measure the magnetic field with our flux gates, but there could be in the ADCs, again, a magnetic field temperature dependence and so on. So the direct mechanism is not really clear what is the implication, but it's clear that temperature has to do with it. Okay. So I told you that we can measure the V cross E effect, and this is actually a nice thing because now we can have actually a handle to really measure the electric field that the neutrons actually see. So what we did here is we on purpose misaligned the electric and magnetic field. You see this here in an illustration on the right side here. And we did this by giving a small transversal magnetic field, or adding a transversal magnetic field, and then scanned the high voltage. And then we get this Ramsey phase shift up minus down beam. as a function of this high voltage, and this actually fits nicely to what we would expect. So the neutron see really this well, in this case, -40 to +40 kilovolts per centimeter. And then we played, obviously, we put the field in this direction, in that direction, we changed the amplitude of the fields and whatnot, and just to see, and then optimized also that we have no V cross E effect. And there was lots of things you can play with when you have this handle. And then if you want to measure an EDM, which we also did, but we first emulated this by changing the magnetic field. So what I show you here is for the top beam as a function of the neutron wavelengths, so as a function of the time of flight, for our set magnetic field of 220 microtesla, you see that this plot that I showed you, this curve that I showed you before, is actually nicely flat, right? We are, for all neutron and wavelengths, we are perfectly on the same resonance. The sinusoidal signal looks always the same. And then when we change the magnetic field, in the case of the red curve or red dots data points here, we reduced it by 1 microtesla. In the case of the green dots, we increased it by 2 microtesla. And you see that the slope changes upwards and downwards, just as we expected. And this means, and this is also easily to understand, so the neutrons with the higher wavelengths are slower, and they spend a longer time in the magnetic field. So they also accumulate more phase. So that's why they, for instance, at 1.5 angstrom, 1.5 nanometer, they accumulate like 360 degrees, while these one at 5, they only accumulate 100 degrees. And in the end, if you extrapolate, they actually really meet at 0. And what you would do now in a real EDM measurement, or what we did in a real EDM measurement, you set this on this black line, 220 microtesla, and then you flick the electric field, and you check if the slope is changing. This is what you basically do.
What are the fluctuations in the spread of the data points? Is this somehow related to this serial experiment?
Well, this is purely statistics. So this is not any systematics that you see at that, because this is like I don't remember how long this measurement took, but maybe like 10 minutes or so. Okay. One of those measurements, because this is a full scan of this data points on the phase Ramsey. So this is not just one working point, but like several, and one measurement takes like 10-15 seconds or so, and then we scan this for like 20 points or so.
But in the UCN experiments, the co-magnetometer is very, very important.
Mm-hmm.
So here you
we don't have a co-magnetometer, right? No. Would be interesting to have an option for some magnetometer. It's not yet clear what we could do there. We're thinking of water, flowing water, tubes that pass by. I mean, in the end, yeah, one has to see. At the moment, we're working just with flux gates, right? And then we see if we can get something better. So the entire thing is proposed for the proposed ANI beam line at the ESS, which is still in the proposal phase. So it's not yet clear that this will be actually built, but this is how this more or less looks like. So you have here the target monolith of the ESS, and then you have several guides in this S shape going to your experimental area, and this is like 25 meters long. So we could work with like a 20-meter long setup, but this has also an extension potential, so that we could actually go to this 50 meters as mentioned. So in this real scenario, so I want to come now, what are the perspectives for the ESS? What can we expect there? What sensitivity and so on? You have to take something into account when you have a pulse source, and this is that, for instance, the ESS pulses with 14 hertz, and that means if you go over a very long distance, like 75 meters or so, these pulses can overlap. So the previous pulse can overlap with the next pulse, and so on and so forth. So in order to have to achieve that you don't have pulse overlap, you have to limit your wavelength spectrum. And you can do this in various ways, but in the end, you can come up with some numbers like from 3 to 7 angstrom or so. Then you would have nicely separated. You have no overlap, and this is like the time, and here's the distance. And if you plug in numbers, so ESS is expected to have similar peak, similar average intensity as the ILL. And so what we did is we used the ILL data and also ESS simulations. I will tell you maybe later on a bit to extract the beam intensity or the beam brightness, and then you plug in numbers like the visibility of your Ramsey signal. We achieved like 90%, but I put here like 75%. Then the length of 50 meter and electric field of 100 kilowatt per centimeter. And then you can make a back of the envelope calculation of the brightness or the rate that you would expect. And you go in from the particle brightness that you have at ILL, for instance. This is this 10 to the 13 per square centimeter per second per Stehradian. And then you say, okay, you lose because you want to polarize your neutrons, you lose a factor of 3. Then ESS should be equivalent to 1 to ILL intensities. And then you have your cross section of the beam, 2 beams, each 20 square centimeters or so. And then if you just say that you have an aperture here and then another aperture 100 meters away, and you don't expect that the neutrons are guided in any way by electrodes or so, but just you have an aperture here, 100 meters away, another aperture there, you just lose by the solid angle, right? And this is a drastic loss, obviously, 10 to the minus 7. And then you end up with something like 40 megahertz. And then this would give you something like 2 times 10 to the minus 25 electron centimeters per day. But then you would say, okay, you have absorbing electrodes, but in the end, you have electrodes that go all the way, and the neutrons, they're actually getting reflected by these electrodes. And assuming a gain factor due to this of about 10, due to this reflections, you end up with 5 times 10 to the minus 26. So why do I come up with this factor 10? That's a bit random, right? It's not completely random because we tested actually the reflectivity of our electrodes. And if you compare the scenario with the absorbing electrodes, you see that you only allow a divergence of 0.02 degrees or so that go through. But if you have these electrodes and you measure the reflectivity, so this is this black curve here for our diamond milled electrodes that you see here on the side, then you end up actually with reflectivities beyond 0.2 degrees. So this is this factor 10 that I mentioned. So instead of losing all the neutrons that just diverge away, you can guide them and you can gain a factor 10. And actually, this is also, we could also show this by first max test simulations that we did with the ESS package. And this is ongoing research. So I don't actually know how much time we have.
Basically, 5 minutes, but you can keep going.
Okay, then I'll show you
later. So go ahead.
Okay.
No problem.
Okay, sure. So what is the current status and next steps? So we performed this proof of principle experiments at PSI and ILL, and we also performed the first EDM measurements. We only took like 24 hours of data or so for the EDM. The rest was really all systematic checks and playing with all these angles and playing with magnetic fields and so on and so forth. The idea is to have a future competitive full-scale experiment intended for the ESS. And what we're currently doing now is, as I said, these max test simulations, which actually are looking very good for the ESS, actually better than what I showed you there. And we also end up then with very high rates of neutrons, right? We'll have hundreds of megahertz, and this is a challenge. And so we are also looking in just a new PhD student has just started, and we're looking into new options for high rate detectors. Okay, I want to show you a slight different thing, something that Kent also already touched upon, and this is axions and ALPS, which is also coming a lot of times with the neutron EDM, also people doing axion experiments. And you probably know all about this and the strong CP problem and why they were introduced. I just want to say that obviously there's a large variety of axions and axion-like particles now around, and also lots of experiments who look for very specific axion and axion-like particles. And one possibility is that the axion-like particle that interacts with via the gluon with a gluon, and this would induce an oscillating neutron EDM signal. And so therefore it's interesting to look at the neutron EDM as a measurement, as a function of time. This is what PSI did, for instance. We were looking at, in the NEDM data, we're looking at fluctuations as a function of time to see if there's some oscillating EDM signal, which could be a signal for an axion-like particle. So in this beam time that I showed you before, we also did this measurement. And because we have a beam, we changed from the pulsed mode, we changed to a continuous mode, and we did continuously sampling all our neutron data, and basically we can measure an EDM with a very high frequency. In order to know how sensitive we actually are to such an axion, what we did is we induced so-called fake axion signals by applying a real magnetic field with an oscillating signal, with an oscillating magnetic field signal. And from that, we could extract the sensitivity of our apparatus to magnetic fields, right? So I show you an example, maybe then it becomes a bit more clear. So before I showed you, here this is the neutron asymmetry as a function of time. So before I showed you, we measured this very often, and then we get a nice straight line, and then there was just this drifts and so on. But now we intentionally applied an oscillating magnetic field, here 0.5 hertz and here 5 hertz. And then our neutron asymmetry fluctuates exactly with this frequency. And from that, we can extract, like, okay, we know how much field we apply, because we measured this previously with a mapper, with a magnetic field mapper. And then we can say, we can translate magnetic field into a symmetry. And then we could do the other way around and get from a symmetry to an axion field or so. And we sampled the data with like 4 kilohertz. So, and we injected fake axion signals from DC to 1 kilohertz or so to see how sensitive we are. And what we did then is we look at the spectrum and of our data. Here's some example, and then you see, for instance, this typical 50 hertz peak, right? We will always get from the mains power supply, and then you see this kind of signal. But then you have also other conditions that when you look at the two beams, then because the electric fields are opposite direction, they should be this axion signal should be just out of phase. And there should be also no signal if the electric field is off. So you can switch it off, and then there should be no axion signal. And this is actually here the result, which has just been submitted to PRL, and it's on arXiv. You can find it. And this is the plot. Here you see the mass of the axion or the oscillation frequency. And here the interaction strength or the coupling. Here's the neutron EDM data, which goes to this inverted to 1/300 seconds. And then here's the electron EDM data, which goes up, goes up to 0.4 hertz or so. And this is our new result that goes to approximately 1 kilohertz. Yes. I would have something else, but I think I skipped this. So we're also working on go ahead. Okay, sure. It's just a few more slides. Sorry. So just one little other things. We're also working on neutron interferometers, and the idea is here to measure the neutron electric charge. The current limit is 10⁻21 electron charges, which is very, very small already. And what you basically do there is you make a very nice collimated beam, or what you did there in the 80s, you make a very nice collimated beam, and check if you apply a transversal electric field in this direction, that direction, if the beam moves left or right, right? That's basically the idea. And you can do this a bit better by using an interferometer and by using 3 absorption gratings. So we have here these 3 absorption gratings for neutrons G0, G1, and G2. And this is in the so-called Talbot-Lau configuration, where they are all identical gratings and they have identical distances. So the G0 is basically making from a non-coherent beam a coherent beam, or you get coherent line sources, let's say. Then the G1 is then the grating where the diffraction happens. And at the position of G2, your interference pattern would appear. But since this interference pattern is very tiny, like micrometer size, you cannot, with current standard neutron detectors, you cannot resolve this. So what you do is you introduce a third grating, this G2, with the same period as your interference pattern, and you scan this, and then you get you can scan this through. And by this, you can then also look for change of your interference pattern if it moves left or right due to applying electric fields transversely to that. And this is our setup. We set this up in May in 2022. It's about 4.5 meters long. Here are the 3 gratings: G0, G1, G2. Vacuum tubes where electric field should go in. At the moment, there's nothing in there yet. It's just vacuum. Here you see these gratings on a quartz wafer. This is gadolinium coated, and then laser engraved gratings, very small gratings you can produce there. And then you obviously have the most tricky thing is the alignment of the entire thing. This is really where it takes time to align and to get rid of moire patterns and all these things. Right? But nevertheless, we had some nice success, and we could see some nice interferometric scan here with this. And this is what's going on. And this is my summary. So I showed you the new complementary neutron EDM experiment. I showed you a bit of the axion search that we did, and just a very brief look at this neutron interferometer work. Thank you.
Thanks, Florian. That's really, really exciting. Questions?
Very nice. So now you're the second person showing that the mu metal shield at high frequency reduces the shielding factor. Kent also showed that. Do you have an idea about that, why that happens?
Well, we don't have an RF shield. That's maybe one thing. This is just mu metal.
You have RF shield. But even a mu metal should.
Yeah, even mu metal should. I mean, we have a specific geometry. Maybe that's the reason. But yeah, but so we also go into 1 kilohertz. Down right? Again. But this is typically what you would expect, that you have some peak and then it goes down again. This is what I know from Alad, for instance, that he showed in some of his talks, that you expect some peak at 20 hertz and then going down again. And that it doesn't go down is due to RF shielding from an additional copper or whatever. Yeah. Yeah. No, but other than that, I don't have an idea why this is the case.
There's questions. Skyler, you can go ahead.
Yeah, thanks. Okay, so I share Philip's curiosity over the shielding.
1 second, because you're not. Yeah. We cannot hear you. Just 1 second.
Where is it coming out? Is it here? Maybe if he says it again, I can repeat the question partially. Or
yeah, we can do that.
Yeah, can you hear me, Florian?
I can hear you.
Yeah, okay, so thanks. I share Philip's curiosity over the shielding, but actually the question I wanted to ask is one that I received many times from colleagues at the ILL about this velocity range between ultra-cold neutrons and cold neutrons. So obviously there's a balance between statistics and measurement time, but with all of these ongoing thoughts about developing VCN sources, also for the ESS, one can imagine an EDM experiment using a beam of very cold neutrons. And it's not immediately evident to me if this would be a gain or a loss. I think for the statistics point of view, one can argue this based on the spectral brightness and the beam divergence. This falls out from the guiding, but what's more interesting and less obvious to me would be the impact on systematic errors, because this V cross E correction is kind of at the heart of your experimental concept, and that will work very differently in different velocity ranges. So to what extent do you know the global optimum velocity range, let's say, and if it's not what you would already use, then in which direction would it lie?
Okay, that's a complex question, I would say. So so I don't know about the statistics you would expect from a VCN source. So I know something about the PF2 VCN source. I mean, you have to be much better than that, I would guess. An important thing to point out here, I think, when you think about this, is that you want to have a velocity range rather than a velocity, like a certain velocity, right? For instance, because you want to extract the slope, like I show in this slide, the longer the range is, in this case, it goes from 0.3 to 1.5 nanometer. The longer the range is, the better your slope determination is, right? So if you just, for instance, have just a bright, high monochromatic VCN source, that doesn't help you. You would need to have something. The ideal thing would be something where you have VCNs and cold neutrons coming out. So you have you can really get a point at VCN and a point at cold neutron spectrum.
But then you have a problem with frame overlap, or you have to skip a lot of pulses.
Sure. Then you cannot build it so long, and then there's as you say, this is optimization problem, and then this. I have not looked into that in detail, I have to admit, but I was always working with what we have, which is cold neutron sources.
Sure. Thanks.
Yeah.
Oh, yes. Well, I was going to say, for that, then gravity plays a big role. If you have lots of reflections and some might be non-specular, then you get very different walking paths. Yeah. But on the code magnetometry, I was going to suggest, and I know that tube of water was at Jeff Green, or other people have done that, but have you considered molecular beams or atomic beams?
So maybe two things. So in an initial publication, I think I mentioned that actually why you don't use 4 beams of neutrons.
Yeah.
So that would go in the direction of a mercury EDM, where you have 2 beams that really measure the EDM, and the 2 outer ones would measure the gradient. But this makes it obviously much more complex, again, more complex experiment. So what we have here, for instance, is this tube of water that we, similar to what Jeff Green did. So we have here a mu metal shield and a simple mu metal shield, and a flow of water going through here. And this is a commercial NMR system. Okay. So we are actually working on that already, but there's issues because the length becomes an issue, because you have T2 times or T1 times of 1 second or so with water. So you have to pump the water quickly through. So with this 1 or 1.5 meter setup, this works nicely, and you get nice signals. We can make nice Ramsey curves, and is
that with the E field?
No. This is just okay. It's hard to see. So this is actually the polarizer. So the water flows through here, meandering through a high magnetic field, and then goes into a glass tube inside this mu metal shield. And then there's 2 pi half spin flippers. And then we can do all this Ramsey kind of things that we want to do. And then our spin analyzer and detector, so to say, is this NMR system. And we use this mainly as a test bed for developing ideas. You can access this 24 hours a day if you want. You can let this run. It's just water. It's a very simple thing. And you're very sensitive, actually, to picotesla level and below. And you can get really nice Ramsey signals. And we looked at stuff like Bloch-Ziegert shift, applying different kinds of RF signals, and using 4 spin flippers and 3 spin flippers and whatnot, right? This is, you can easily access this, put stuff in, put it out. And then if you're confident that this would help you with something, then you could maybe implement this into a neutron setup. This is much easier to assemble and to use.
I don't know. Think of a helium-3 vapor beam. You pre-polarize it with MEOP or something, and then you can get it. 500 meters
I
per
know they-
second. And
Mhm. Yes, but they would ideally they would go in the same path as the neutrons, right? Which, well, I don't know. Well, I don't know. Maybe there's options, right? At the moment, this thing is already cluttered full of cables. And it's not so much space in there. And you need time for development, right? Now, I have not looked into that.
More questions? I have a question about your 5 times 10 to the minus 26 per day. Sorry, I need to know
Yeah.
these numbers. So, so how long do they let you use the beam?
How long? What?
So, I mean, this means that you can use the beam for 24 hours, and that's the sensitivity that you will get.
Yes.
Yeah. So if you apply, if you have a proposal, I'm assuming you apply.
Well,
How
there's
much-
not yet even a beam line there. That needs to first to be.
So again, so a $10 million question. What would be the timeline then in this case, if you have an idea?
So there's still some. I mean, there's some basic things we have to figure out, like how do we actually would detect such a large amount of neutrons. That's why we're looking into detectors. And our near future plan is to measure again at ILL, or nearer future plan to with an improved setup, right? So we go stepwise. So this is nothing on the timeline of 5 years like PSI, or not even 10 years probably. But it's a complementary experiment, right? That's the advantage.
I completely agree. Yeah, sure. Yeah. Are there more questions? Okay, if not, shall we go and get some coffee? Thanks to speakers.